In Calculus 1, you have studied two ways of calculating the volume of a solid of revolution. Now we're going to look at how to calculate the surface area of a surface of revolution. And instead of rotating just the graph of a function about either the x-axis or the y-axis, we're going to look at rotating a parametric curve about one of the axes. So this is what we've established in the previous video about arc length of parametric curves. In the case where we have a parametric curve that is traversed exactly once as t increases from the initial value of the parameter a to the terminal value b, and the curve is smooth, and then the arc length of the corresponding curve is given by the integral from a to b of the square root of the sum of the squares of the derivative of x and of y. And we're going to use this fact in obtaining a formula for the surface area of the surface of revolution generated by rotating such a curve, to start with, about the x-axis, just like here. So what does it look like? If you pick a point on this parametric curve and you rotate it about the x-axis, then you generate a circle like that is centered on the x-axis in the three-dimensional space. And if you do that for each point on the curve, you generate a surface of revolution like that. So this is the surface that we're looking at, not the solid, and so just the shell. And we want to know how to obtain the value of this surface area. So we're going to proceed just like we did when we were trying to establish a formula to calculate the arc length. We're going to split the interval of the parameter t in n subintervals and focus on a particular subinterval, for instance this one from tk to tk plus 1. And if we rotate this part of the curve around the x-axis, we obtain something like that. Now we're going to try to get an approximation of the surface area of what we obtain, and then sum these approximations for k ranging from 0 to n minus 1. So let's look at this and try to approximate its surface area. This length here is, well, the arc length between tk and tk plus 1, and proceeding just like we did when we were looking for arc length, we can approximate that by the square root of the sum of the squares of delta xk and delta yk multiplied by delta tk, where delta tk is simply tk plus 1 minus tk, delta xk is the difference in x values, in other words f of tk plus 1 minus f of tk, and delta yk the difference in y values, in other words g of tk plus 1 minus g of tk. And now if I pick a sample point in the interval from tk to tk plus 1, let's denote that tk star, and I look at the corresponding point of parameter tk star and rotate that point about the x-axis, I get this type of circle. And here I also drew the radius of that circle. And you see that the radius is really the y value at tk star. So this really corresponds to this circle drawn on the surface of revolution that we have generated by rotating the piece of the curve corresponding to the interval of parameter from tk to tk plus 1. So we're going to use that to approximate the surface area of the surface of revolution. Namely, we're going to, you see that here you have this blue circle, and then the length on the side is delta sk, but it is not straight. So we're going to approximate the surface area by the surface area of the cylinder, where the base is a circular base, and it is the same blue circle that I have drawn on the red surface of revolution, and the height is the same length as the red part of the curve from tk to tk plus 1, in other words, delta sk. Now the surface area of a straight cylinder is something easy to obtain because, well, here I just want to mention that we are using the same circle, and therefore the radius of the circle that we use as a base for our cylinder is y of tk star. And to obtain the surface area of a cylinder, you can unfold that cylinder into a rectangle and just look at the length of the size of this rectangle. If you unfold it, then you see that on top the side is going to be the circumference of the circle, in other words 2 pi times the radius, which is y of tk star, and of course the height is unchanged and is in this case delta sk. So we obtain, when we unfold our cylinder, we obtain a rectangle with these two sides, delta sk for the height and 2 pi y of tk star for the length. And now that means that to approximate the surface area of our full surface of revolution, we're going to approximate it by the sum of the surface areas, which are given by the areas of these types of rectangles. And therefore we obtain an approximation by taking the sum from 0 to n-1 of 2 pi times y of tk star times delta sk. And we know what kind of formula we would have for delta sk. And you see that in the usual way we have something that is akin to a Riemann sum for the function 2 pi y multiplied by the square root of the derivative of x squared plus the derivative of y squared. And therefore we're going to actually define the area of the surface of revolution as 2 pi times the integral from a to b of the function y of t multiplied by what we would have for the arc length, in other words the square root of the sum of the squares of the derivative of x and y, and we integrate against the parameter t. So this is what we would obtain taking the limit over all subdivision as the parameter of the subdivision for the interval of the parameter goes to 0. So we have this formula, and if we look at what would happen if we were looking at rotating a parametric curve about the y-axis instead of the x-axis, you see that the only thing that would change is that this radius here is now x instead of y, so that means that this y here in our formula would have to be changed to x. And this is the only thing that would change in the considerations that we just encountered. So we have these two situations where when we have a rotation about the y-axis, we're going to get 2 pi integral of x times ds, in other words this integral of the sum of the squares of the derivative of x and y. And if we rotate about the x-axis, we have 2 pi integral from a to b of y times ds, in other words root of sum of the squares of derivative of x and derivative of y, integrating all of that against the parameter t. So let's look at one example to illustrate that. Here we want to find the surface area generated by rotating the curve of parametric equations x equal e to the t minus t and y equal 4e to the t over 2, where t ranges from 0 to 1. And we are looking at the rotation about the y-axis. We're going to just admit that this is a curve where the curve is traversed exactly once as t increases from 0 to 1, and therefore we can apply this formula. Because we are looking at a rotation about the y-axis, then the radius for the rotation is x, and so we get that the area is 2 pi integral from a to b of x of t times ds. This is the formula we've established before in the case of a rotation about the y-axis. So now we're just going to plug in the values for a, b, x, dx over dt, and dy over dt. So a is 0, b is 1, x is e to the t minus t, its derivative is e to the t minus 1, and the derivative of y, when we differentiate e to the t over 2, we get 1/2 e to the t over 2, therefore the derivative of y is 2 e to the t over 2. Multiplying things through for the squares, e to the t minus 1 squared is e to the 2t minus t to the t plus 1, and 2 e to the t over 2 squared is 4 e to the t over 2 squared, which is e to the t. If we simplify what we have under the square root we have e to the 2t plus 2e to the t plus 1, and that is in fact the square of e to the t plus 1. So now when you have square root of a square, you get the absolute value of what you have under this. But in this case, what we have under the square root of a square is e to the t plus 1, which is a positive function. So I obtain simply e to the t minus t multiplied by e to the t plus 1, which I integrate from 0 to 1, and then multiply by 2 pi. If we multiply things through in the integral, we obtain e to the 2t plus e to the t minus t e to the t minus t. There are three of the terms that we can integrate directly, for which we can give an antiderivative explicitly, immediately. These are e to the 2t, e to the t, and t. Namely, an antiderivative of e to the 2t is 1/2 e to the 2t, antiderivative of e to the t is e to the t, and antiderivative of minus t is minus t squared over 2. What remains is that we have to subtract the integral from 0 to 1 of t e to the t. And that can be simplified using integration by parts, where we're going to differentiate t and integrate e to the t. And doing so, we obtain for the integral from 0 to 1 of t e to the t dt, using integration by parts, we get t to the t evaluated from 0 to 1, minus the integral of e to the t, which is just going to be minus e to the t evaluated from 0 to 1. So we obtain 2 pi multiplied by this expression that we are going to have to evaluate between 0 and 1. And the value at 1 turns out to be e squared for 1/2 of e to the t. Then we have plus e minus 1/2 minus e and plus e. And all this simplifies as e to the t minus 1 over 2 plus e. On the other end, the value at 0, when you plug t equals 0, 1/2 e to the 2t is 1/2, e to the t is 1, then t squared over 2 is 0, t to the t is 0, and e to the t is 1, and that simplifies as 2 plus 1/2. Writing everything in the parentheses with denominator 2 and cancelling this 2 with the 2 pi, we obtain pi multiplied by e squared plus 2e minus 6. And that is the value of the area of the surface of revolution obtained by rotating this curve about the y-axis. Now it's time for you to do some homework.